What if I told you there's a fundamental rule that connects everything from a roaring fire to the very thoughts inside your head? Well, today, we're going to crack the code on that law, and it all starts with what looks like a simple puzzle, balancing a chemical equation.
So let's just jump right in with a big question. What if a simple equation, just a few symbols on a page, could actually break a fundamental law of the entire universe? It sounds a little dramatic, I know, but in the world of chemistry, it's a puzzle we have to solve every single time.
And that puzzle leads us straight to a universal law. This is an unbreakable rule that's in charge of every single chemical reaction, whether it's a log burning in a fireplace or the millions of processes happening inside our own bodies right now.
This rule has a name, and it's a big one. The law of conservation of mass. It states, pretty simply, that mass can neither be created nor destroyed in a chemical reaction. Basically, you can't just make stuff appear out of thin air, and you can't have stuff just vanish.
So what does that really mean when we're looking at our equations? It's actually pretty straightforward. The number of atoms for each element has to be exactly the same on both sides. The inputs, what you start with, have to perfectly match the outputs. It's like the universe's way of balancing its checkbook.
Here's an easy way to think about it. Imagine you're shuffling a deck of cards. You can mix them all up, you can deal out new hands, but no matter what you do, you're always going to have 52 cards in that deck. The atoms are just like those cards. In a reaction, they just get shuffled around and rearranged into new molecules.
Okay, so theory is great, but let's look at a real-life example. Here we've got a chemical puzzle, an equation that right now is actually breaking that universal law we just talked about. Our job is to fix it.
So here's our puzzle. Magnesium plus oxygen reacts to form magnesium oxide. If you've ever seen this reaction in a science class, this is the one that creates that super bright white flash of light. But take a close look at the formula. Something's not quite right here. Let's take an inventory.
Okay, on the left side, the reactants. We're starting with one magnesium atom and two oxygen atoms. Got it. But then look at the right side, our product. We have one magnesium, and wait a minute, only one oxygen atom? An entire oxygen atom has just disappeared. And as we just learned, that's a huge no-no. It's impossible. This equation is unbalanced.
So, how do we fix this? We can't just let atoms vanish into thin air. We need a toolkit. So let's go over the simple but really powerful rules we have for solving this chemical puzzle.
Our main tool is something called a coefficient. That's the big number we're allowed to place in front of a molecule. You can think of it like a multiplier. It just tells us how many of that entire molecule we have. This is the only thing we're allowed to change. Now, that little number, the subscript, that's part of the molecule's identity card. You can't touch it. If you change the subscript, you change the entire substance. It's like turning water, H2O, into hydrogen peroxide, H2O2. Totally different things. So rule number 1, never ever touch the subscripts.
All right, we've got our toolkit, we know the rules, it is time to solve this equation. And the good news is, there's a simple, repeatable process we can follow every single time. Here is our roadmap. Step 1, write the unbalanced equation. We did that. Step 2, count the atoms on both sides. Done. Now for the really important part. Step 3, we add coefficients in front of the molecules to get the atoms to match up. We'll just do it one element at a time. And that leads us to the final, crucial step. Check your work to make sure everything is perfectly equal.
So let's apply this. We started with 2 oxygen atoms on the left, but only 1 on the right. To fix that, we'll put a coefficient of 2 in front of the MgO on the right side. Great! Now our oxygens are balanced, 2 on each side. But, that also gives us 2 magnesium atoms on the right now. But that's an easy fix. We just go back over to the left side and put a 2 in front of the Mg. And just like that, the puzzle is solved.
Let's do our final check, the moment of truth. On the left side, we have 2 magnesium atoms and 2 oxygen atoms. Now on the right side, we have 2 magnesium atoms and 2 oxygen atoms. It is perfectly balanced. The law has been obeyed. Nothing was created, nothing was destroyed. Everything is accounted for.
So you might be wondering, okay, cool, but why do we go through all this trouble? It's a fair question. Let's zoom out to the big picture and see why this is so much more than just a classroom exercise.
First and foremost, we balance equations to obey that fundamental law of the universe. But on a practical level, it's what allows us to show the correct recipe, the right quantity of substances we need for a reaction. This is absolutely critical for any kind of real-world chemistry, from baking a cake
to creating life-saving medicine. It makes all the calculations possible, and maybe most importantly, it ensures our equations are an accurate reflection of reality.
So think about this for a second. Every single chemical reaction in the universe, from the birth of a star to a single thought firing in your brain, plays by this exact same rule. Everything has to balance. The only question left is, what will you balance next?